Okay, this is a simple example. We're going to show based on the mass of the Earth and radius of the Earth, which is a mean radius rather than the radius at a particular location. As I mentioned in the previous video, the Earth is an oblate spheroid, so it's actually, if you think about it, it's closer to get to the North Pole than it is to get to the equator, because it's been squished out a little bit, so it's fatter around the middle. So we're going to use the average radius of the Earth to show that g really is 9.8 meters per second squared. Or, to be more precise, normally we'd take 9.81. We're going to get a little larger than that, but it's still going to be pretty close. So, to do that, the magnitude of gravitational acceleration will be big G times the mass of the Earth divided by the radius of the Earth squared. The mass of the Earth, I've taught this class a long time, folks. I've got a lot of things memorized. It's 5.97 times 10 to the 24 kilograms. Yes, you should be given that on a formula sheet if it's used on an exam. I'll have to remember that when we get there. Radius of the Earth, I mentioned in the last one, but it's 6.37 times 10 to the 6 meters. Big G, if you haven't got that memorized yet, I do encourage you to try and memorize it, although hopefully you get it through use without having to put much effort in. 6.674 times 10 to the minus 11 newtons meters squared per kilogram squared. All right. Why does this matter? Well, we've got a new model of physics. We've got a new model of how gravitation works. But the old model and the new model need to be consistent under conditions like the surface of the Earth. If they're not consistent at the surface of the Earth, that means one or the other model is really doing a bad job. So there needs to be this continuity in science. So let's find out. 6.674 10 to the minus 11 times 5.97 10 to the 24. And then divide by 6.37 times 10 to the 6 and square it. And we get little g is 9.819 meters per second squared. I did tell you it comes out a little closer to 9.82. Again, we are using the mean radius of the Earth. If we were using one specifically at the equator, it would probably be closer to 9.81. If we were using one specifically at the North or South Pole, we might get something a little larger than 9.82 even. But there you go. All right, well that was short. I'm going to go on and do one more problem that is a little bit more of a practical one. So come back for the next video where we do a second practice problem.